Welcome back, everybody. So we are going to continue here. So now I'm about to, yes, thank you. Sorry about that. So we are going now to pull the rabbit out of the hat and show you that we are going to land about right where we were a few weeks ago. And so we are going to be using this. So remember the assumptions that we've been doing right here. We have been assuming that the contingency table doesn't depend on the query, right? PK is the same as PKQ. You can remember that with Pokemon Wisdom, right? Pika, Pikachu, PK, PKQ. And so then we made a few other assumptions. And so here, the idea is that for the non-relevant document, we assume it's just as good as the internet. And so we use the document frequencies. And for relevant documents, we just assume maybe it's here, maybe it's not here, right? And so when you don't know something, you just put 1/2, 1/2. And so this is what we have right here. And so if we smooth, if we round a little bit more, we can even take n right here, right? You agree? The document frequency, if you look at the entire internet, the document frequency for most terms is very small, if you ignore the stop words. So we put n in here. And so now what we can do is take this and plug it right into the CK formula, right, with the PK and UK. And we get this. We get this. Log of 1 is 0, right? Okay. So log of 1 is 0. That goes away. And then we have logarithm of the document frequency divided by n. How do we get rid of the minus in front of the log? We put it inside. So to the power of -1, take the inverse, and we get this. This is incredible. Who is amazed at seeing that? What is log of n divided by the document frequency? Did we see that somewhere? That, yes, we do. I see a bit of nodding. Where did we see it? That is the inverted document frequency, right? That's the IDF. That is the inverted document frequency. So it is incredible because we made all these assumptions, and at the end, we are just adding some sums that contain the inverted document frequency. So what we have just done with this mathematical derivation is that we have given a justification to the use of IDFs in the vector space model. That is what we have done. That justifies, with the probabilistic approach, it basically says that putting the IDF in your vectors in the vector space model basically is consistent with ranking documents by decreasing relevance, by probability of decreasing probability of relevance. That is the result here. And this is really huge to come back to that. So this basically corresponds, there's no term frequency, right? So this would correspond to an instant of the vector space model where we don't use the term frequencies, we just put zeros and ones, Booleans, that exist in smart, right? In the smart menu, I can say for the term frequency, I put 0 or 1. So if we do that on both sides, and on the query side, we don't have IDF, on the document side, we have the IDF, and we don't normalize, then we get exactly the retrieval status value of the probabilistic information retrieval model. It's all connected. Probabilistic information retrieval, the vector space model. All right. So this is great, right? This really, really is a great result. For the term frequencies, we also need to justify them. That will be the next lecture. And then the term frequencies will also pop right out of the hat, but in a different lecture. Then we'll have a justification for both. All right. And so yes, when I say, you just put the Booleans instead of the term frequencies, so that would be BTN, BTN, the smart code for the two, something like this. Maybe not quite, because that would put the IDF on both sides. So the IDF needs to be on only one side. Maybe I'll fix the code. But anyway, you see the idea. We accumulate the evidence. We go through the terms that are in the query. We go through the postings, which are the documents that contain the term, and we accumulate the IDFs into the buckets. That gives us the status, retrieval status value. And that you know how to do. We've done that. We've seen at the beginning the intersection algorithm, then we see term at a time, document at a time, you know, all the ways to accumulate this. This is unchanged. The only thing we are tweaking is the term in the mathematical sense term, right? What you add. We change what is added, in this case, the IDF. Who is with me? Right? So it feels great, right? To just land right on our feet where we have what we've seen before. Now, I would like to finish with one more way, a different way of implementing that instead of this theoretical work that was done on a blackboard, a different way to estimate PK and UK. This is known as OCAPI. OCAPI was, I think it's the 90s. That is an information retrieval system that implements all of that. And BM25 is, BM means best matching, right? Best matching. Best matching is basically this whole idea of matching with term frequencies, IDFs, and so on, instead of just the Boolean approach, right? So it's called, this is a whole class of systems. Best matching, 25. I don't know why 25. Maybe I can try to also find out why they called it BM25. All right, so here's what they did, slightly different. What they did is that they considered that this 1/2 here for filling the PK, 1 minus PK, is an outrageous assumption. It's just too simplifying, right? That's too coarse, and so they were not very happy with it. It might be a bit exaggerated that the odds are 1, meaning 1/2. So instead, they said, this 1/2, instead of that, we are going to evaluate it with real people. So the elves in Antarctica, they don't exist, right? I hope it doesn't disappoint anyone, but we have real people who use your system, who connect and input queries. So if you are a search engine with users, then you can actually ask your users. And so the way that it works is that a user inputs a query in the system, and then the query is executed, and then we use some values. At the beginning, you might put 1/2 if you want, right? To just bootstrap the system, you put 1/2. But at step K, more generally, we are going to call them PK. At step S, sorry, so S is the step. And we display the results to the user, right? We show the results to the user. And we ask the users to mark the relevant documents, right? So it's manual work. We ask the user, please tell us. You see that, right? When you go to some websites, you're on some support website, and then suddenly there is a pop-up. Did you find this page useful? Right? You see that over the internet. It's actually done in practice. And so they ask the users to mark relevant documents. And so it means it goes into relevant, non-relevant, R and R, relevant, non-relevant. And based on that, you can do some statistics, again, maximum likelihood estimate, right? You take the answers of the users, you look at what they stamped as relevant, all the ones that are relevant. Of them do not contain term K, right? You just accumulate everything that is stamped as relevant, even across queries, because as I said, this Pikachu thing, we just don't care about the query. We aggregate the statistics and we compute the ratio of containing term K over everything that is relevant. That gives us an updated value, a newer value. I put an S+1 in there to say that. That's a better value because now it takes into account the feedback. And then we just do it again. We cycle, right? We do another step. So here's how we update it. Now, I told you about smoothing. So again, the same idea, we can just add this 1/2 and this 1, that just to smooth things out, right? To account for the fact that maybe you don't have enough users for the statistics to be very relevant. Some other people, instead of smoothing with just 1/2, they smooth with the previous value. Who has ever heard of a Kalman filter? Never. It's a way of smoothing, basically, when it's used, for example, for a GPS or navigation coordinates, when you keep having a point where you are, but you know the GPS, it's not very precise, right? So if you just look at your point, it might jump a little bit. And so if you want to plot the path on which you are, when you follow the GPS coordinates, instead of taking the next value, you interpolate it with the previous value. It's a way of smoothing the path along which you move. That's called the Kalman filter. And so this here is a little bit like this. It's like you have this brand new value that you're about to compute of your PK, but instead of just jumping to it directly, or instead of just smoothing it with adding 1/2, you give some inertia from the previous value, right? It's like you keep an anchor to the previous value so that you don't go away too much from the previous value, just to keep it a bit smooth, right? For whom is that clear? Right, so this is why we add this pk here. Kappa, it's just a Greek letter that is a constant. It's a parameter. So for kappa, you can just put whatever value you want, or you can use machine learning or whatever to optimize it. All right. Maybe machine learning is an overkill for just one variable, maybe. But anyway, so we just keep updating the new value. And this is like a Bayesian update. Remember the umbrella and the rain? If I give you new information that I have my umbrella and then ask now, how does it affect the probability that it's raining? Well, going from S to S plus 1 becomes a Bayesian update, right? So this Kalman filter approach is a little bit like this. All right? And so now I have updated them. These are the posteriors, right? The priors at step S, posteriors at step S plus 1. And now I just do it all over again. I just keep updating. And so if I'm lucky enough to have a popular search engine with a lot of people, then of course, the quality of this is going to improve. And yeah, that's how it works. And that was the last slide of probabilistic information retrieval. Do we have any questions? Anything that wasn't clear that you want to ask? Don't hesitate, because if something wasn't clear to you, it's very likely it also wasn't clear to others, right? So there's never anything wrong about asking questions. Any questions? On Zoom, questions? Last chance? Okay. So if you still have questions that come later, just ask them on the forum, send us emails, send us messages, and we'll be happy to answer them. You can also ask each other, right? It's the best way to learn is to teach. So if you ask others to teach you, they can also learn by teaching. Because when you teach, it forces you to, you realize what you don't know, it forces you to go there and specifically focus on the gaps. All right, well then, for this one, for the probabilistic information retrieval, we are done. And again, what is the most important message in here is that we got back the IDF. We got back to the vector space model with the inverted document frequency. Historically, the vector space model came a bit later, right? So Boolean retrieval, then probabilistic information retrieval, 60s, 70s, 80s, and then the vector space model came a bit later than the probabilistic retrieval. I think the vector space model was the SMART system, was one of the first. Yeah, but it's already old. I mean, it didn't come that much later than probabilistic information retrieval. So I'm going to stop the recording here, then I'm going to jump to the other slides.